Listen to that. Catastrophic structural breakdowns. That's a line straight from aeronautical engineering research. And it's a pretty stark reminder that in the world of aerospace, the stakes, well, they couldn't be higher. We're talking about the very integrity of flight itself.
Welcome to Next Gen Manufacturing Nexus. Today, we're going to dive deep into a massive shift that's happening right now, how we're moving from just reacting to failures to actually forecasting them before they even happen. It's a revolution that starts at a microscopic level, but trust me, it has huge consequences for all of us.
So, to really get the solution, you first have to appreciate the sheer scale of the problem. And we're starting in one of the most demanding places on Earth, the aerospace industry. Think about it.
Every single flight an aircraft takes is this intense sequence of high-stress events. From takeoff to cruising at 30,000 feet to landing, all those forces add up, hour after hour, creating something called metal fatigue. It's this slow, invisible weakening that is incredibly hard to track. Remember that idea of wear and tear? Because we're going to see it again on a much, much smaller scale. And this number is why it all matters so much. A single complex part for an airplane, like a piece of an engine, can cost over 150,000 euros. So if a tiny microscopic defect gets created while it's being made, or if it fails later on, the cost is just astronomical. Not just in money, but in the potential for disaster.
Okay, so let's zoom in, way in, from that plane in the sky right down to the factory floor. Because the battle against failure really begins here, in the microscopic world of high-precision machining, where these critical parts are actually born.
At the heart of all this modern production is a technology called high-speed machining, or HSM. The idea is pretty simple, really. Just work faster. By cranking up the cutting speeds, you can make parts with incredible precision, and you can do it way more efficiently. But all that speed, it comes at a price.
And this is where the physics gets kind of crazy. At these speeds, you're generating blistering heat and just violent vibrations. This whole environment is basically a full-on assault on the cutting tool. It wears it down, and it risks damaging that super expensive component we were just talking about.
And this right here, this shows you exactly what happens. On the left, you've got a perfect, pristine tool. On the right, a tool that's been absolutely destroyed by chipping and fractures. A tool that looks like that isn't just worn out, it's actively creating flaws in the very part it's supposed to be making perfect.
So, you've got this brutal, high-speed battlefield inside the machine. How do you fight back? Well, the first line of defense is just smarter engineering, tackling that heat and friction head-on.
This chart tells such a powerful story. Look, if you just run the machine dry, on the far left, your tool lasts maybe 5 hours. But watch what happens when you get clever with cooling. You use something like cryogenic cooling, and suddenly that jumps to 25 hours. And with the latest nanofluids, you're looking at 30 hours. That's a 6-fold increase in the tool's life. That is a massive game changer for efficiency.
And no, this is not science fiction. This is what that tech actually looks like. A cryogenic system basically blasts the cutting zone with supercooled liquid nitrogen. It flash freezes the point of contact to fight back against that insane heat. It's a brute force solution, for sure, but man, is it effective.
But here's the thing. Physical solutions are only half the story. The real revolution, the next-gen part of this, is building a layer of digital intelligence on top of the machine. It's like giving it a nervous system that can sense, understand, and supervise the entire process.
So how do you build this digital nervous system? Well, it boils down to a pretty straightforward 3-step playbook. First, you have to sense what's happening. Then, you standardize all that information so it can be understood. And finally, you use that data to supervise the whole operation in real time.
It all starts with data. You basically give the machine senses. You embed a whole network of sensors right into the machine to listen to everything. The forces, the tiniest vibrations, the temperature spikes, even the high-frequency sounds the cut makes. The machine is no longer the silent, dumb worker. It's constantly telling you exactly how it's doing.
But all that data is completely useless if every machine is speaking a different language, right? That's where standardization comes in. Standards like ISO 1339 acts like a universal translator. It creates a common language for everything about the tool, so the machine, the software, and the engineers are all on the same page.
Okay, so you've got the senses collecting data, and you've got the universal translator to make sense of it. The final step is the brain, the supervision, and that is a tool condition monitoring system, or TCM.
Think of it like a doctor, constantly checking the tool's vitals. It analyzes all that data to give a live diagnosis of its health, and it knows the difference between normal wear and the first warning signs of a total failure.
And this is where it all comes together. This is the magic moment. When you combine those smarter physical systems with that digital nervous system, you stop just monitoring the present. You can actually start to predict the future.
And the ultimate expression of this whole idea is the digital twin. It's a perfect virtual replica of the physical machine that lives in the cloud. It pulls in all that real-time sensor data and uses it to run simulations, predicting stress, wear, and potential failures before they ever have a chance to happen in the real world.
Now, this isn't just a theory. Check this out. This is a real-world machine learning pipeline built to predict the fatigue life of an entire aircraft wing. It takes this impossibly complex problem and breaks it down into 3 steps you can actually understand. First, it predicts the stress. Then, it predicts the damage from that stress. And finally, it calculates the component's total lifespan.
So how does an AI even learn to do something like that? Well, you make it practice, millions and millions of times. These graphs basically show the AI's error rate while it's training. It's like watching a student get better and better at a test. As those lines drop closer to the bottom, the machine is getting smarter, more accurate, and better at its predictions. You're literally watching it learn.
So what does this all mean? When you put all these pieces together, what do you actually have? Well, it's a fundamental shift in how we even think about making things. It's a move from an old way of doing things to a brand new one.
So, what's the big takeaway here? At the end of the day, we're moving away from a reactive world where we basically run around like firefighters putting out fires after things break. Instead, we're moving to a predictive world where intelligence and data let us prevent the fire from ever starting. It's the difference between foresight and hindsight.
And that leaves us with a pretty fascinating question to think about. This whole incredible system we just looked at was built to forecast the failure of one tiny cutting tool. If we can master that, what's next? What else can we predict? Supply chains? Market demand? The future of making things isn't just about building them better, it's about knowing what's coming next.